Hello everyone, I'm Gyewon from Seoul National University and FriendliAI. In this talk, I'm going to present to you our paper, Refurbish Your Training Data, Reusing Partially Augmented Samples for Faster Deep Neural Network Training. Deep neural network training is an important task for deploying deep learning-powered applications. Broadly speaking, a DNN training pipeline consists of the data preparation and the gradient computation. During the data preparation procedures, the training samples are read and pre-processed for gradient computation. Such data preparation procedures are usually done on CPUs. On the other hand, during the gradient computation procedure, weights of deep neural networks are adjusted by forward and backward operations. Because such operations are computationally expensive, they are usually executed on their accelerators with massive hardware parallelism such as GPUs and TPUs. Their computation time can be overlapped as the two procedures are executed on different devices. The heavier computation needed for the gradient computation had made it the main performance bottleneck for DNN training. However, as recent DR accelerators become incredibly faster, the data preparation procedures are becoming a new performance bottleneck. To investigate this problem, we look into how data preparations are performed in more detail. The training samples are first read from the storages and go through decoding and formatting procedures. After that, the samples undergo data augmentation and are collated to make a batch of augmented samples used for gradient computation. We focus on data augmentation, which is a widely used technique to enhance the accuracy of the trained model with a limited amount of data. Data augmentation applies random transformations to training samples in order to provide more diverse samples during training. This figure illustrates a state-of-the-art augmentation pipeline, RandAugment. The augmentation pipeline consists of multiple layers of random transformations. Because each layer applies randomly chosen transformations, an augmentation pipeline can generate an exponential number of augmented samples. Such multi-layered augmentations are useful, but they often cause heavy CPU overhead that slows down the entire DNN training pipeline. From the next slide, we will investigate the actual impact of such overhead with an evaluation. We have measured the training throughput of Reson 50 trained on ImageNet using varying number of RandAugment layers. As an evaluation environment, we use a Docker container with an NVIDIA V100 GPU and 4 physical CPU cores. Here is the evaluation result. When there are only random crop and random flip layers, the training throughput reaches the maximum gradient computation speed of the GPU. However, when the number of RandAugment layers becomes 2, the training throughput is cut in half. The throughput further decreases as the number of RandAugment layers becomes bigger. As we have seen in this result, DNN pipelines can be bottlenecked by excessive CPU overhead caused by data augmentation. Now, the question is how we can reduce such overhead from data augmentation. One recent approach is data echoing, which caches and reuses previously materialized samples to accelerate slow data preparation procedures. This approach is useful for training tasks with slow I/O, such as training pipelines whose training data reside on remote storages. So, the question is, would this approach still be useful when data augmentation becomes the main bottleneck? Unfortunately, the answer is no. For better understanding, we first illustrate the standard training with an augmentation pipeline. Since the stochastic augmentation is independently applied, a unique augmented image is used for gradient computation for each epoch. In case of data echoing, the samples are cached and reused after the augmentation. So in the second and the third epochs, the augmentation pipeline is not executed. However, data echoing severely degrades the diversity of augmented samples as the same augmented samples are used for multiple epochs. This results in low accuracy of trained models, as we will show in the evaluation. To address this problem, we propose data refurbishing, a simple but efficient mechanism to reduce the CPU overhead from data augmentation. This figure illustrates the high-level concept of data refurbishing. Unlike existing approaches, data refurbishing splits the augmentation pipeline into the partial and the final augmentation, and caches the partially augmented samples. Since each partially augmented sample is refurbished by the stochastic final augmentation, it can produce a unique augmented sample in each epoch while reducing computation overhead. We demonstrate the effectiveness of data refurbishing with a mathematical analysis. We define the sample diversity, which we denote U, as the number of unique samples that are generated during training. Note that our goal is to preserve U, while reducing CPU overhead from data augmentation. We also define the cardinality of the augmentation A as the augmentation diversity, which indicates the number of unique augmented samples given a training sample. The cardinality of AF denotes the augmentation diversity of the final augmentation. R and K denote the number of reuses for each cached sample and the total number of training epochs respectively. Given such parameters, the expectation of sample diversity can be calculated as shown in this slide. We visualize the equation in a 3D plot. The x and y axis represent the reuse factor and the final augmentation diversity relative to that of the total augmentation. The z-axis represents the relative sample diversity compared to the standard training. We set the number of training epochs to 300 and use RandAugment for the augmentation pipeline. We first plot the sample diversity of the standard training. As we can see from the plot, it has the highest sample diversity but will suffer from low training throughput because it does not cache or reuse augmented samples. Second, we plot data echoing. In this case, we can observe that the sample diversity severely degrades even with the lowest reuse factor of 2. This results in low accuracy of the trained model, as we will show in the evaluation. Last, we show the sample diversity with data refurbishing. This figure demonstrates that if the final augmentation provides enough diversity, the data refurbishing can maintain almost the same sample diversity as the standard training. These results also give some hints on how to make a good split strategy. A good split strategy should ensure enough final augmentation diversity while minimizing the computation overhead from the final augmentation. Now, we explain how we realize the data refurbishing through our new data loading system, Revamper. The challenge in realizing data refurbishing is that the actual throughput gain can be limited due to poor computation overlap between CPU and their accelerators. This happens because CPU processing time may fluctuate according to the number of cache misses, whereas gradient computation time on the DL accelerator remains almost the same. To solve this problem, we propose Revamper. Revamper supports two distinguished features, the balanced eviction and the cache-aware shuffle. The two techniques help balance the number of cache misses across the epochs and within an epoch, respectively. For better understanding, we first explain the architecture of PyTorch Dataloader. It consists of the main and worker processes. The main process sends the shuffled indices to workers. Each worker then reads the corresponding training samples. After that, the training samples are augmented and sent to the DL accelerator. Revamper is different to the traditional data loader in that it includes a cache store and the training samples are handled differently according to whether they are cached or not. Before starting each epoch, the evict shuffler from the main process selects the samples to be evicted from the cache. This ensures that its training sample is only used for the designated number of times. Within a mini-batch, some indices are cached, whereas the others are not. For the cached samples, the worker reads the partially augmented samples from the cache store and applies only the final augmentation to save the computation overhead. In case of cache miss, the worker reads the original samples from the data store and applies both the partial and the final augmentation to them. During the augmentation process, the partially augmented samples are stored to the cache store so that it can be reused in the future epochs. Now, we explain the balanced eviction, an eviction algorithm that balances the number of cache misses across epochs. First, we assume that Revamper adopts a naive reference count algorithm. In the second and the third epoch, all the training samples are cached and thus data preparation can be done very quickly. However, in the first epoch, cache miss occurs for all the training samples. This unevenness can cause suboptimal computation overlap between the CPU and the DR accelerator. To solve this problem, we propose the balanced eviction. After the first epoch, a designated number of samples are chosen by the evict shuffler. The number of samples to be evicted is calculated by dividing the number of training samples by the reuse factor. The evict shuffler adopts sampling without replacement so that all the indexes get a fair opportunity of being evicted. Even with the balanced eviction, CPU processing time may still fluctuate due to the randomness of data shuffling. In this figure, the cached samples flock to the second mini-batch, and this results in unnecessary waiting between the CPU and the DR accelerator. With the cache-aware shuffle, the cached and non-cached samples are uniformly mixed inside each mini-batch. By making the cache-miss ratio for each batch constant, computation time of the CPU and the DR accelerator can be overlapped in an optimal way. Because Revamper selects both cached and non-cached samples in random orders, such modification does not affect the accuracy of the trained model. Now, we move on to the evaluation. Revamper is written in about 2,000 lines of Python code based on PyTorch 1.6. It overrides the existing PyTorch Dataloader with the identical interface, except for some additional parameters, such as reuse factor and the split strategy. We evaluated Revamper on a dedicated training server. Same as the earlier motivating evaluation, we adjust the CPU-GPU ratios using a Docker container. As an evaluation workload, we used image classification models. Other than the standard training and data echoing, we evaluate one more setting, the simplified, which simply removes one or more layers from the augmentation pipeline. Notably, we use the same hyperparameters of standard training for all settings, which demonstrate the effectiveness of Revamper without additional hyperparameter tuning. First, we evaluate Revamper and the other baselines on ResNet 50 with ImageNet dataset, along with RenderAugment. Revamper has shown better training throughput compared to the standard setting, while maintaining comparable accuracy with negligible 0.05% accuracy drop. When we set the reuse factor to 2, Revamper shows 1.59 times better throughput compared to the standard setting, and shows 2.04 times better throughput when the reuse factor is 3. On the other hand, data echoing shows lower validation accuracy even with the lowest reuse factor of 2. This is because data echoing harms the diversity of augmented samples because it directly reuses the fully augmented samples unlike Revamper. The simplified setting also shows substantial accuracy drop, demonstrating that simply removing augmentation layers does not provide good trade-offs between training throughput and model accuracy. We also show the training throughput change on varying number of CPU cores. Revamper shows better throughput improvement when CPU resource is relatively scarce. As the performance of their accelerators rapidly increases, we expect that more training jobs will benefit from Revamper in near future. So here's the conclusion. Data refurbishing is a new intermediate data caching technique for DNN training, which accelerates data augmentation while preserving diversity of augmented samples. Revamper realizes data refurbishing in an efficient way by maximizing computation overlap between CPU and their accelerators with carefully designed cache eviction and shuffle strategies. In our evaluation, Revamper improves training throughput of DNN models by up to 2.04 times while maintaining the comparable validation accuracy. Thank you.